We've seen that a conductor shields an external electric field. So basically the external electric field bends to be perpendicular to the conductor's surface, and the conductor effectively acts as a Faraday cage with a zero electric field inside it. And this here is known as electrostatic shielding, where the electric field is shielded from entering the conductor. So electrostatic shielding can also be visualized by having an electric field due to a charge inside the conductor. So imagine that these are two conductors that are thick shells that are concentric with each other, and this is a section through both conductors. So the electric field due to this point charge is going to be radial, but bend to be perpendicular to the surface of the conductor. Okay, so it's going to look something like this. So it's more condensed near the charge. And this must be the case because there must be no electric field inside the body of each conductor. So given that there's no electric field inside the body of a conductor, then the electrons are going to develop on the surface of that conductor to prevent that electric field from entering the body of the conductor. So therefore, if you can imagine constructing a Gaussian surface through the body of the conductor, so this is a spherical surface, then the net charge inside that Gaussian surface is zero. So remember that the electric flux is the closed integral over that surface, and we integrate the dot product between the electric field vector and the area vector, and that's equal to the total charge enclosed in that surface on the permittivity of free space. So therefore the charge due to those electrons on the surface of the conductor is going to cancel out the positive charge, and therefore the net enclosed charge in that surface is going to be zero. So therefore the flux through that surface is also zero, and there's no electric field in the body of the conductor. Now due to electrons developing on the bottom surface of that conductor, so that's going to leave behind positive charges on the other surface of the conductor. So therefore this conductor is going to act like a point charge, producing an electric field that emanates radially from it. So all around that surface. And consequently, electrons are going to be attracted to that positive charge. So you're going to have on the inner surface of the other conductor a bunch of electrons that are going to shield the body of that conductor from an electric field. So remember that the electric field inside a conductor is zero, and consequently when you have those electrons developing on the bottom surface, they're going to leave behind positive charge on the other surface. Okay, so the net charge on the outer surface here is plus Q, which is equal to this charge, and the net charge on the inner surface of this conductor is minus Q, and then plus Q, minus Q, plus Q. Okay, because if you construct a Gaussian surface in the middle of that conductor, you have a charge of plus Q, minus Q, plus Q, minus Q. So the electric field inside the body of the conductor is zero. And that's the most important idea. And I'll see you in the next video.